Hi, thanks for tuning in. In this video clip, I describe the proof of Theorem 6.2 in this paper. The theorem in question says the modified von Mangold function is a pseudo-random measure, or in other words, it satisfies the linear forms condition after going through what is called the W trick. So let's recall the definition of the modified von Mangold function and the statement of the theorem. Let me see. So here is the definition of the von Mangold function. So R is a positive real number and chi is a C-infinity function which has values between 1 and 0, and we assume that it has a compact support, and for the normalization reason it's convenient to assume that the support is between -1 and 1, and at the origin it should have positive value, but let's assume that it's 1. And then we define, so this is a function from non-zero ideals, or zero ideals. So this is my symbol to denote non-zero ideals. So let's allow zero ideals too, and the value is a non-negative real number. The definition is, so if you give an ideal here, its value is log r times, so the ideal b dividing your a, and the Möbius function and the function chi evaluated at the norm of your ideal b divided by log r. It's good to remark that so this exceeds 1 if your ideal has norm larger than r, and there are not so many, not infinitely many such ideals. So the number of such ideals is proportional to r. So in any case, so there are only finite many of them. So this is always well defined. And for later use, I define a constant c chi to be the integral of the derivative squared, and this is of course positive. Yeah, now I can state the theorem. So there are hypotheses, a lot of hypotheses. So m and t are positive integers. M is the number of linear functions you consider, and t is the dimension of the source. So these are linear maps, z linear maps, and I assume co-kernels are finite. In practice, you will only encounter a situation where the co-kernel is trivial. So namely, all the maps are surjective. And the kernels don't have inclusion relations. And next, the w is a positive parameter, and large W is an integer whose prime divisors are precisely the positive prime numbers, not exceeding your small w. Yeah, and I1 to IT are intervals long enough intervals, and I define a box to be their product. So this is a large enough box, Now if R is large enough, so the threshold is determined in terms of M and the number field, and W should also be large enough. The threshold is determined by size, and R should grow faster than W in the sense that this ratio should be small enough. Then we can compute the following average. So this is an average inside the box you have defined, and we take the product of something. That something is your modified for Mangold function, and I consider the linear map here. You multiply it by W and slide it by BI and take the square. Oh, so this is me in the post-editing process. I forgot to mention what BI is. BI is an element of OK, the ring of integers, which is prime to capital W in the ring OK. So the product should be from 1 to m because there are m linear maps. And we consider these values. This can be evaluated. So the main term is times 1 plus errors. Sorry, I forgot the power here. Yeah, therefore, if you divide by this function, then this guy will satisfy the linear forms condition. And here, so this phi is the tangent function in the context of a number field. Whenever you are given a non-zero element of your ring of integers defined to be, you take the residue field, residue ring, the multiplicative group of your ring, and take the number of this finite set. Yeah, this is the statement. Yeah, maybe it's good to draw a picture. So this is the domain of the linear maps, and this is OK, and we have a function here. I mean, when you put an element inside this function, you are considering the principal ideal generated by that element. Yeah, I mean, it's actually squared, and also w. Yeah. So you again go to OK by W and slide. So it's slided. And this slide can be different, but in practice we will use a common amount of slide. And there are a bunch of linear maps here too. And you are taking a large enough box somewhere around here and taking the average. Yeah, I mean, it's difficult to grasp what is going on. So anyway, let's try to prove it. Yeah, the story begins with unfolding the quantity that we are looking at. So let's start the outline of the proof. So the quantity to be computed is this guy. That's the definition. And I can, let me see. This log r. This log r can be taken outside, so it will be make it easier to read. To the power of 2m. And next I expand the square to get and you take the product of your function. So if you also consider this product, this will become so this is the sum over the choice of I is from 1 to m, and k is either 1 or 2. And yeah, and so this condition we will treat it as a characteristic function which takes value 1 only when the condition is met. So I take the product of k1 2 and I1m, and bik should divide. Yep. So very complicated. So I'm taking this average, but we note that the only thing that depends on x is this characteristic function now. So this is the benefit of writing the condition not inside the sum, I mean not inside sigma, but outside sigma. So that's the benefit. Okay. Yeah. And the sum is all over here. All over. And now we will begin the estimate of this average.